Hi, in this question, we want to find all natural numbers n such that n squared does not divide n minus 2 factor, right? So what exactly is a factorial? So a factorial is a continued product from a specific number till 1, right? So what if we want to calculate n factorial? What we need to do? Like n factorial will be the product from n to n minus 1 till we arrive at 1, right? So like 4 factorial will be 4, or we can write in this from the reverse also, like 4 into 3 into 2 into 1, which is 24, or we can write it in the reverse like 1 into 2 into 3 into 4. So this is the concept of factorial, right? So like let us see. So if we choose n to be 7, so what is n minus 2? It's basically 5, right? So like what is 5 factorial? It's basically 5 into 4 into 3 into 2 into 1, right? So it's like 120. Okay, and what is n square here? Since n is equal to 7, so n square is 49, right? So now if we try to divide n minus 2 factorial, that is 120, by 49, what we should get? It's like the quotient will be 2, it's 98, right? And the remainder is 2. So 120 is not divisible by 49. So this is a solution to this question. So if we choose n is equal to 7, we will see that n minus 2 factorial will not be divisible by n square, right? Okay, so let us generalize this result. So in this question, we have to find all such natural numbers such that this does not divide n minus 2 factor. So the fundamental thing here is to think what form a number can be, right? So like if a number is 6, we can write it in the form like 2 into 3. So there is a fundamental theorem of arithmetic which states that so every number can ultimately be factored into prime factors, right? So like 18 can be written as 3 into 3 into 2, right? So ultimately any number can be prime factor, right? This is the fundamental theorem of arithmetic, right? So we will use some these like not the exact fundamental theorem of arithmetic, but because for large numbers the like the numbers of factors will be very large and it will be like very difficult to verify. So what we can do to minimize our time, we'll see some special forms of the number, right? So that will cover all the possible numbers, and if we prove the theorem for all these possible sorts of number, then we will prove the theorem for a general number n, right? So let us see what I am talking about. So suppose this is the total number set, that is this represents all the natural number. So like any natural number, we are trying to find some particular forms of n, right? So first thing is that so any natural number n can be written in this form, right? So it can be written as p to the power k, like it can be like 3 or like 9 or 27. So all these type of numbers are coming in this form. So this is a part of this whole natural number system, the numbers which are of the form p to the power k, like so like 3 is here, 2 is here, 4 is here, 8 is here, 27 is here. Okay, so these are containing all the numbers which are of the form some prime put to the power k, right? So k is basically another natural number which is raised to the power k. Okay, so what other forms of number can be? So like n can be of this form also, so product of two natural numbers p and q, right? So like these are the numbers that are of this form p and q. Okay, so like 2 into 3 6, 7 into 3 21, right? And say 7 into 11 77, right? But 7 into 7 is not here, 7 into 7 is here, because 7 into 7 is 7 square, which is of this form p to the power k, right? So this is another subset of this n, which is of this form pq, right? So what other numbers can n can be? So n can also be of this form, right? It can be also of this form p into q into r, where P and Q are prime and R is any other number that may be or may not be prime. Okay, so basically what remains is will go into this form, right? Because suppose if the number is of P, it comes here. If the number is like PQ, then it comes here. Or suppose if we think of this number like of this form, like P to the power, let's say k1 into q to the power k2. So you may think that such type of numbers will not belong to any of this, but if you see closely, this can be written as p into q into p to the power k minus 1 into q to the power k minus 2, right? So basically if this k and k2 are quite large, so this number will be greater than 1. So obviously this will belong to this group, like p into q into r. So you can see that any natural number, if you select, either it will be falling into this group, that is the p to the power k group, or it will be falling into this pq group, or it will be falling into this group pqr, right? So we will now try to find the solution to our question for each of this form, right? So we are asked to find, so how many natural numbers are there among all these natural numbers which does not divide n minus 2 factor, right? So we need to check, so what kind of numbers in this form pq are there which does not divide n minus 2, and equivalently in this form pq are there which does not divide n minus 2 factorial. And if n is of this form p to the power k, then how many numbers are of this form are there which does not divide p minus k? So if we independently solve all these three cases, then we can find the general form of all such natural numbers which will ultimately not, so whose square n square will not divide n minus 2 factor, right? So this is the first fundamental approach to such kind of questions, right? So now let's see how you can proceed with each form, right? So let us now take these three cases one by one. So first we assume that n can be of this form pqr. Obviously since p is a prime number, so p can be like greater than equal to 2, and q is a different prime number. So since 2 is taken, so we can like assume to be like greater than equal to 3, and r is at least 2, because if r is 1, this is of this form pq, which is again the second form we are thinking, right? So these are the basic assumptions about this form, right? So what is n square? N square is p square q square r square, right? So what we can do is like, so here is 1 2 and here is say n minus 2, this is n minus 1 and this is n, which is of this form pqr. What we can do is like that, so we can find some distinct numbers which will collectively give you p square q square r square, right, between this one and n minus 2. So let me explain. So we can write this as p into q into pr into qr, right? So this product gives you p square, then q square and r square, right? So one thing you may ask, that how I got these four numbers, right? So this comes from experience, right? So if you are doing such kind of problems for long enough, so you can like, so do some trial and error, and you can like find the appropriate factors of this, how these numbers can be dealt with, right? So now if we can prove that this p lies somewhere here, q lies somewhere here, pr lies somewhere here, and like qr lies somewhere here. So if all those four numbers lie in between 1 to n minus 2, then obviously their product, which is n square, will also lie between this n minus 2, and automatically this square will divide n minus 2 factorial. Okay, right? So let's see how we can prove that these all numbers are less than n minus 2, right? So n minus 2, what we can do is will be greater than n minus p, right? Because p2 is the smallest prime number, so p is generally larger than 2. So what we can do is that we can substitute n with this form pqr, which is n minus p. Now you see that what is the minimum value of this possible. So because p q is 3 and r is 2, so q and r can have a minimum value of 3 into 2, which is 6, right? So this can be greater than or equal to 6p minus p, because we have put the minimum values of q and r. So obviously this number will be greater because this is the minimum value possible, right? So which is 5p, which is obviously strictly greater than p, where 5p is greater than p. So we can see that what we have proved is that p is less than n minus 2. So p lies somewhere between 1 to n minus n. So here can be p, right? Similarly, we can show for q, because n minus 2, which is obviously greater than n minus q, because q is 3 at least, which is pqr minus q, which is again we can say it's greater than, so p is like the minimum value is 2, r minimum value is 2, so it's like 4q minus q, which is 3q, which is obviously greater than q, right? So what we have got, that q is less than n minus 2, right? Now we can do for same for pr, like n minus 2 is greater than n minus pr. This will like give you pqr minus pr, right? So if you take the pr as common, so this is q minus 1. So as q can be minimum 3, so it's like 3 minus 2, this is 2, right? So this is greater than or equal to pr into 2, which is strictly greater than a single pr, right? And similarly, we can prove the last inequality. So n minus 2 is greater than n minus qr, which is again pqr minus qr, which is qr into p minus 1. So this p can be 2, or this is strictly greater than or equal to qr. So this is 2 minus 1 1, so it is strictly greater than 1. So what we can see here, that all these individual numbers, that is p is less than n minus 2, q is less than n minus 2, r, say this pr, so this is less than n minus 2, and qr is less than n minus 2. So what we have shown is that this p, q, p and q all are lying between n minus 2. So when we will do n minus 2 factorial, so once always you will get p somewhere else, q somewhere, you will obviously get pr somewhere, and you will get qr somewhere, and then it will stop at n minus 2. So this is the all are multiplied, so p, q, pr and qr. So this whole factor, which is p square, q square, r square, will obviously be a factor of this n minus 2 factorial, and will automatically divide n minus 2 factorial. So there can be no number of this form pqr which can divide, so whose square can divide n minus 2. So will not divide n minus 2, because always its square will divide n minus 2 factorial, right? So if this number is this of this form, right? So this was case 1. Okay, so now we come at the second case. So in the second case, what we can see is that our number will now be of the form p and q. So first we take a special case when p is 2, right? When one of the prime number is 2, then the number is of this form 2q, right? So what you can see here is that, so the number line again I am drawing, so 1, 2 till n minus 2, right? So here somewhere there is q, right? Because q is smaller than n, so something will be like q. So n is, so since p, n is of this form 2q, so this last number here we will get a 2q, right? So like here we have got one q, and here we have got 2q, right? So you can see easily that in this time frame, so since q is first appearing here, so all these numbers are less than q, and since q is a prime, so q will not appear anywhere in below this, like in the left side of this number. And similarly, the next factor of q, so if q is a prime number, the next factor to immediate factor will be 2q, which is again beyond n minus 2, right? So we can conclude that, so between all these numbers 1 to n minus 2, the only one factor of q, which is q itself, will occur only once, right? So q square, so q will divide, so since q is here, so q will obviously divide n minus 2, because since there are no other factors of q, so q square will never divide q n minus 2 factorial, right? So this factorial, so n minus 2 factorial. So what we can see, so if the number is of this special form 2q or 2 times a prime number, then obviously this n square will not divide n minus 2 factorial, right? So we have got one part of the solution. So we are slowly like collecting the solution. So one solution can be, if n is this form 2 into some prime number, then obviously n square will not divide. So actually not divide can be symbolized as this, so will not divide n minus 2 factor, right? So this is a part of this solution. So this is the first solution we have got. So now we have to check for a more general thing, which is PQ, right? So now we are assuming the general form where n is of this form PQ. Since we have assumed one of them to be 2, now we can assume that both P and Q, so they're like, we can assume without loss of generality that this Q is greater than P and P is like at greater than 2. So at least it's 3. So like P is minimum of 3 and Q is like minimum 5, right? So this we can assure from this relation, right? So now let us see what we can do from this problem. So what we can show here is that, so again we use the same inequality. So n minus 2, this can be again written as, this is greater than n minus p, because p is at least 3. So this n is of this form pq, so pq minus p. So a similar thing what we have done in the previous case, so which is p into q minus 1. So since q is at least 5, so this is like greater than or equal to 5 minus 1, that is 4p, right? So what you have seen is that this 4p is less than n minus 2. And similarly for q, if we do, we will get, so this to be n minus q, this is again pq minus q, this is again q into p minus 1, and like p is the minimum value is 3, so 3 minus 1 is 2, so it's greater than or equal to 2, right? So what you have seen that this, sorry, so this will be 2q. So this both 4p and 2q both are like less than n minus 2, right? So this paves the way for this like particular conceptual understanding that this one here is 2, so somewhere there is p, right? Because the last number is like 4p, okay, and the previous number is like 3p, and since p is at least 3, so here only two numbers are there, so one number is there between, that is, so like, so this n minus 2, so it's like pq, right? So these two numbers, so p is somewhere between and q is somewhere between, so these two numbers which are like 2q and 4q, so these are like less than n minus 2, so this will lie between this, so somewhere here, right? So somewhere, so here maybe 2p is there, or somewhere here like 4p is there, and somewhere between 3p is there, so here 2q is there, so somewhere there will be 2q. So we can see that this p is also here, and another factor of p is also here, like, so p square will always be a factor if we take this from 1 to n minus 2, right? Because all these numbers are like less than n minus 2, and since q is a factor here and 2q is also present here, so q into q square is also a factor here, so this p square and q square will divide n minus 2 factorial, right? So we have assumed n to be pq, so we can conclude that this n square will also divide n minus 2 factorial. So let's update our solution. So along with like so there is no actually no updation in the solution, because we want to find all the numbers that will not divide, so this will divide, like, so till now we have got only one solution, so the number which are of the form 2p, their square will not divide n minus 2 factorial, right? So now let's do case 3, right? So it's the case where the number is of this form p to the power k, right? So p is a prime, it's only a product of some k prime, the same prime k times, right? So let's how we can do. So suppose we can consider this line. So 1, 2, 3 till n. Here is n minus 1. Here is n minus 2, right? So like it's p to the power k. So and let's suppose that somewhere here there is p, okay, and then there will be 2p, right? So how much it can go? So like as the largest number is p to the power k, so the next, so the number just which is less than p to the power k is like p to the power k minus p, right? So which is like p to the power k minus 1 into p, right? So this 1p 2p and it will go up to till p to the power k minus 1 minus 1 into p. So what we can conclude is that, so in this expression, so there are p to the power k minus 1 minus 1 these times p are there. So exactly this number of p's are there in the expression, right? So if this number, so as there is k times p and n square is like p to the power 2k, so if so the number of p's here is like greater than 2k, then you will have exactly 2k number of p's, right? So if this number is greater than 2k, so then there are, so like the number of factors of p are like greater than 2k, then what will happen is that, so then easily this, so if we like group this 2k p's together, then you will see that this p to the power 2k will divide this n minus 2 factor, right? So we will have that n square divides n minus 2 factorial if this the number of like p to the power k minus 1, so this is greater than 2k, right? So we focus on the case where this will be less than 2k, right? So this p to the power k minus 1 is less than 2k. So what happens this if this gets less than 2k, right? Okay, so you can see, so like if k is greater than equal to 5, so let us suppose that this k is greater than 5, so then the smallest prime number is like 2, right? So what we can see is that this p to the power k minus 1, this expression will be actually greater than 2 to the power k minus 1, right? Because this 2 to the power 2 is the smallest prime, so any p must be greater than this 2, right? So let's see why I have taken this k is greater than equal to 5. So if you put 5 here, so then this is like 2 to the power 5. So actually 2 to the power 5 minus 1. So this actually goes to like 2 to the power. So it's like 15, right? So 15 is actually, so k is here 5. So 15 is actually greater than this 2 into k, right? 2 into 10, that is 25, that is 10. So if k is greater than or equal to 5, then obviously this, so like if you take more like k is more, so if you take 6, then it's like 2 to the power 6 minus 1, so that is 31. So 31 is obviously greater than 2 times 6, right? So that is 12. So you can easily see that when k is, so you may prove it by using mathematical induction, so that's very easy. So whenever is k is greater than 5, so this expression is actually greater than 2k, right? So there is no problem if k is greater than 5. So let's see if k is less than 5, then what is the case? So we will check for like k is equal to 1, 2, 3 and 4, right? So first let us take the case when k is 1. So this, if k is 1, then like n is a prime only, right? So p to the power k, so p to the power 1, which is prime. So again you can see, so here this is 1, 2 and here is n, there is n minus 1, there is n minus 2. So suppose p is there somewhere, and sorry, so p, so n is p. So since we have taken from n minus 2 and it is a prime, so none of it, so this p will never come in between, so 1 and p minus 2, because p is a prime, so it will not have its factor like otherwhere except for n, right? So no p will be present in the number small which are smaller than or equal to like n minus 2. So this is one of our solution, right? So if n is of this form k, then we will have this n square, that is p square. It will never divide n minus 2 factorial, right? So we are done with this case. Okay, so now we move on to this case where this k is like we individually check for k is equal to 1, 2, 3 and 4, right? Okay, so we have these two things. So like we want p to the power k minus 1 to be actually less than 2k, right? And we have this n of the form p to the power k, right? So if like we already have shown for k is equal to 1, right? So let's move to k is equal to 2. So if k is equal to 2, so what we have in this expression is p to the power 1 minus 1 is less than 2 into 2, that is 4, that is p is less than 5, right? So p can be 2 or 3, so the prime number that are less than 5. Okay, right? So if p is 2 or 3, then what happens? So like n is like 2 square or 3 square, right? So if n is 2 square, that is 4. So it's easy to check that this n minus 2 factorial is like 2 factorial, which is 2. So n square, so that is 16. It will never divide 2, right? So 2 is smaller than 16, so this will not divide. And if n is like 3 square, so it's like 9, n is 9. So 9 minus 2 factorial, which is 7 factorial. So again we can see this 81 will not divide 7 factorial, right? So this 81 will not divide 7 factorial, right? So it's easy to check, like because 81 has like 4 threes, right? So in 7 factorial there is like the 3 can come from 3 and from 6. So there are two threes only here, so it will not divide also. So like n is 4 and like and n is 9. So these two are also the solutions. So these solutions are coming if you assume this k to be 2, right? So third one is like when you assume k to be 3. So if k is 3, again you use this expression, this inequality p to the power k minus 1, we want this to be less than 2k. So like p to the power 2 minus 1, so this is like less than 2 times k, so this is less than 6, right? So p square is less than 7. So what we have here is that, so p can be only 2, right? Because if p is 3, so 3 square is 9, so 9 is not less than 7. So here we have only p to the power k. So the number is of this form, 2 to the power 3, right? So if n is 2 to the power 3 is 8, then we can check it that n minus 2 factorial is like 6 factorial. So 6 factorial is 720, and this n square is 64, right? So let's try like this. 64 means there are at least 2 8's here, but in 6 factorial the 8 can come from like, it can come from 2, 4 or 6. But see here, the like if 2 is there and 4 is there, so this is an 8. So if 1 8, maximum 1 8 we can extract from this, like so 6 has 2, so maximum like it may be divided by 16, right? So here is 2, here is 2 and here is 2. So or otherwise you can easily check by dividing this expression, and you can see that the remainder will not be 0, right? So it will not be it will not get divided, right? So n is 8 is also our solution, because we want this to not divide this n minus 2 factor, right? So n is equal to 8 is also a solution. And lastly, what we can see is that, so k is 4, when k is 4, what we have is that, so like p to the power k minus 1, that is p to the power 3 minus 1 is less than 8 actually. So p cube is less than 9. So actually here also we have only one solution, that p is 2, because if p is 3 then it's 27, which does not make sense, this inequality. So we also have here p is equal to 2. So now you substitute this p in this expression of p to the power k. So we have 2 to the power, so k here is 4, 2 to the power 4 is actually 16. So let us check if this 16 minus 2 factorial can get divided by this 2 to the power 8, right? So this is n. So n is actually 16. So like it's 256. So let us check if 256 can divide like 14 factorial, right? So now let us check this 14 factorial. So 14 factorial is, so this is like, as I told you, this is 2 to the power 8, right? So in 14 we can like, there is 2, there is also 4, there is 6, there is 8, there is 10, there is 12, and there is 14, right? So here 1 2 will come, here 2 square will come, here 2 is there, here 2 cube is there, here the 2 is there, here 2 square is there, and here 2 is there. So if we take all these 2 together, but see, so number, so the this total fact, so the maximum factor of 2 that you can get out from here is that this is 2 plus 1 3 4 5 6 7 8, right? So if you take till this only, so it's coming to the power 8. So already this 256 is present in this factor, right? So factorial 14 already contains the 2 to the power 8 or 256. So obviously this 16 square will divide like 16 minus 2 factorial. So this is not a solution. So we have exhausted all the case when the k is like less than equal to 4, and if k is greater than or equal to 5, then we have, so we will have not the, so we will, so this condition will not be met, because for k greater than 5 we have already proven that this expression, this p to the power k will always, like p to the power 2k is always divide n minus 2 factor, right? So what, so overall what answer we got? So like so the solution can be of this form. So what we got, so first case we have shown that if n is like 2p, we will have a solution, right? If n is a prime only, then we'll have a solution, which we got from here, this part. So if k is 1, right? So we have got this n is equal to p, which is also a solution. So p square will not divide it, p minus 2 factorial, right? And thirdly we have got 4, we have got actually what we have got, so n is 8 is there, I think. So 8 is also there, and I think 9 is also there. So but this 4 can be put in this 2p form, right? So if you like want only the general thing, so it's like p, 2p, 8, and 9. So we have exhausted all the forms of n, right? So we have taken into account all the forms which a can have, right? And in all this form we have readily analyzed and saw that these are the only possible way we can have when n square will not divide n minus 2 factor, right? So this is exactly the solution set. So like if you choose p to be 2 or p to be 3 and etc., we can have like multiple infinite number of solutions, but the solution will always be of this form, so right? So thank you, that was it.